Hi, and welcome to this first video in a sequence of videos on data structure lower bounds in the so-called CellProbe model, right? So in this lecture series, it's based on lectures I gave at the Swiss Winter School on Theoretical Computer Science in 2020. Basically, I go over the basic techniques for proving data structure lower bounds. Good. So in this very first video, I'll just introduce the so-called CellProbe model. It's the model in which we prove our lower bounds. And in the following videos, we'll see the concrete techniques for proving them. Right. So first part, what is the CellProbe model? In particular, I'm going to focus on so-called static data structures in this video. So what is a static data structure? I guess the idea or goal in static data structures is to represent some set of input data on your computer so that you can answer queries about the data efficiently. One example could be to represent the road network of a country such as Denmark. So this is your data as a road network, such that given two cities, so this would be a query, you can compute the distance between them along the shortest path. So for instance, this is a simplified version of a road network, and each of the roads have a distance it takes to traverse the road. And maybe you ask a query, give me the length of the shortest path from A to C. And you can see here that the length of the shortest path, or the shortest path is this path here, going from A to B to E to C. And so the distance is 1 plus 3 plus 3, which is 7. So 7 is the answer to this distance query. Now, a data structure, now that several different ways you could solve this problem. Here are two simple ones. The first data structure could just pre-compute and store the answer to all possible queries, right? So there's a query for every pair of cities. You just compute a big table and store all the answers. The second simple solution is to just store the graph as it is. And then when you get your pair of cities, you'll just run, say, Dijkstra's algorithm, any other shortest path algorithm to find the distance between the two cities. Now, the first data structure here is super fast in answering queries, right? It's constant time lookups, but the space is quadratic, right? You store something for every pair of nodes in the graph. And at least for sparse graphs where there's not so many edges, this is very wasteful in space. The second data structure has a very small space usage. You're just storing the graph, so it's linear m plus n, with m is the number of edges, n is the number of nodes. The query time is the time it takes to run Dijkstra. So with a Fibonacci heap, this is something like n log n plus m. So this is much slower query time. So as you see, in static data structures, it's basically a trade-off between the query time and the space, right? We can always pre-compute and store all the answers, but that's going to take a lot of space. So basically, when we have a data structure, the natural question to ask is it possible to solve this data structure problem more efficiently than we have? And so lower bounds basically try to answer this question, right? We want to prove that some trade-off achieved by a data structure is the best possible, right? In particular, that there cannot exist a better data structure, because then we can stop trying to develop them and just use the ones we have. They are the best possible. Okay. So in the next couple of videos, this is the question we'll focus on. We'll focus on how do you actually prove lower bounds, in particular for static data structures to begin with, and then we'll move on to dynamic data structures where the data set can also be updated. And of course, to answer such a question, we need a model of what a data structure can do. Otherwise, we cannot really formally prove anything, right? So this is what we'll introduce in this video. So when you're coming up with a model or defining a model that you want to prove lower bounds, then maybe you should start by asking yourself, what do we want from the lower bounds that we prove? And I think one very nice property would be that if I prove a lower bound for a data structure problem, it holds, the lower bound applies no matter whether it's a PC or a Mac or smartphone that I'm storing my data structure on, right? I want this lower bound in some sense to be universal and to apply everywhere. And I think also a natural thing to ask is that the lower bound should hold no matter what programming language you're implementing your data structure in. And so I think these are good principles for how to come up with a model for proving data structure lower bounds. So you should ask yourself, what is common to all these computational devices and programming languages? And that is one thing that's in common, at least, is that when you're running your data structure, the instructions will be executed by a CPU. And this CPU, when it's executing or performing instructions, it has to access the memory, which is your RAM cache and so on, right? So there's some memory accesses happening where the CPU is retrieving data that is stored in the RAM. And so you could actually say, what is then the memory or the RAM of a computer? Well, basically, it's just a set of memory cells. And for static data structures, we say that S memory cells. Each of these memory cells just stores bits. And here we typically say that W bits in a cell. And the cells also have an address. So basically, it's a big array with that are addressed 0 up to S minus 1. When we prove such lower bounds, it's very common to assume that the number of bits in a memory cell is at least the maximum of log S and log N. And so why is this? It's basically because we normally think of a memory cell as being able to at least store, I guess, to address any input object. If we have n input items, the number of bits is enough to give each item an ID, say the name of each of the nodes in the graph. And also, we assume that a memory cell can store the address of any other memory cell, which basically means it can store a pointer. Right? So that's why we need log S bits. And this also matches with practice, where most computers, at least today, have 64 bits in their memory cells, and maybe 10 years ago they had 32 bits. And that this also allows them to store the address of any other memory cell. Okay. What about the CPU? What can the CPU do? And this is what perhaps varies between different architectures, right? Different architectures might have different instruction sets. But I guess one thing that is common, and this is what we'll be using, is that first the CPU reads some RAM cells into registers. And this always takes at least one clock cycle. It takes some non-zero amount of time to access a memory cell. And then the CPU executes some kind of instructions on the registers. So this could maybe be adding the numbers stored into registers, so they're stored in binary, could multiply them, do bitwise operations, comparisons, and so on. And again, if we ask ourselves, what do we want from these lower bounds that we prove at the end of the day? We want that the lower bound should hold no matter what instruction set you have available on your computer. So in some sense, we don't want to have to worry about what are the concrete instructions that your computer has. We would like our lower bound to hold even if you have any kind of instructions available that you could imagine. So with those things in mind, we can now define the CellProbe model, a model in which we prove our lower bounds. And in this model, a static data structure is really a collection of S memory cells. Each of them stores W bits. W is at least the maximum of log S and log N. And each of the cells has an address from 0 to S minus 1. And the contents of the memory cells encodes the input data. Right. So let's have an example here. So let's look at a concrete data structure problem called the partial sums problem. So the input to the partial sums problem is an array A storing bits in it. Okay, so here's an array. It has bits 1, 1, and 0. Now, the queries we would like to support in this data structure problem is given two indices I and j, return the sum of the bits in the subarray from I to j, right? So the bits in position A of I plus 1, up to A of j. So for instance, a query could ask for the sum of the bits inside this green subarray, which would give the answer 1. Okay. Could also ask for this whole subarray, and the answer would be 2, right? The sum of the bits. Okay. So what could a data structure look like for this partial sums problem? Well, a natural data structure would be to say, well, I store for every index from 0 up to n minus 1, I store the prefix sum, so the sum of everything up to index I in the array. That's what I store in cell I. So if this is my input array, I'm storing the first entry stores the sum of the first entry, the sum of the first 2 entries, and the sum of the first 3 entries. And the numbers here are stored in binary, right? So this is the number 1, this is the number 2, and this is the number 2. This would be a memory representation of this array with a word size of 2 bits per memory cell. Okay. And the space usage here, the number of cells that we are storing, is 3. Okay. If the array looked like this, 0, 0, and 1, then the data structure we would have built with all the prefix sums would be 0, 0, and 1. If the array looked like 1, 0, 1, right, we would store 0, 1, 0, 1, the numbers 1 and 1 and 2 here. Okay, so basically every possible input to a data structure problem is mapped to some memory representation. That's what a data structure is. So now, of course, the data structure also answers queries. And if we say that the query times t, if when we're answering a query, we read up to t of these memory cells, and after reading these memory cells, we announce the answer to the query. And the answer we announce is allowed to depend on the contents of everything we've seen while reading memory cells, right? So basically here we are saying that the computer, your data structure, in some sense has enough registers to remember everything it has seen. And also the cell that you choose to read in every single step of your computation in these t different read operations, they're allowed to depend arbitrarily on the query that you're answering and the contents of all the cells you've seen so far. Okay. So if we want to be formal about it, and this we'll do that in this single video here, but in the coming videos, we'll kind of ignore a little bit this formal definition as decision trees. But if you want to be formal, the query algorithm now is represented by a depth T decision tree for every query. So in this decision tree, each of the internal nodes are annotated with the address of a cell. So that's a number from 0 to s minus 1. Each of the edges that are leaving a node are annotated with all the possible different contents that the cell could have. Right? So if it has 2 bits, then there are 4 different edges leaving it, corresponding to the 4 different bit patterns you could see in a cell. Each of the leaves of such a decision tree are annotated with query answers. So say there's 8 kilometers from city A to city C, what have we? This could be the answer to a query. Now, a query algorithm now, given such a decision tree, is really, you start out at the root, and whenever you're at an internal node, which you are in the root, you read the cell whose address is whatever it's stored on this node, right? So in the node V, you read the cell of address AV, and then you descend into the child who's along the edge that matches the cell contents in your data structure, in your memory representation. And when you get to a leaf, you announce the answer. And you have one of these decision trees for every possible query to the data structure problem. So let's go back to this example of the partial sums data structure. In pseudocode, if you will, or in real code, if I wanted to answer a query with this memory representation where I store prefix sums, I want to answer the query from I to j, so I have to compute the sum of the entries from I to j. One way to do it is to say, well, if I have to sum from 0 and up to j, I just return whatever is in cell number j, right? Because what is in cell number j is storing the sum of everything from the first entry up to entry 0, up to entry j. Otherwise, I return whatever is in cell j, so that's the sum of everything up to cell j, minus the sum of everything up to cell I minus 1, so I subtract off everything that's coming before. Right, so the sum of everything here, if I want to compute the sum of the whole array, the way I would answer my query from 0 to 2 would be to just return whatever is in cell number 2. Right? So that's just return this value of 2, and indeed it's the correct answer. If I wanted to compute the sum of these 2 entries, this would be the query from 1 to 2. My query algorithm tells me to take whatever is in cell number 2, that's 1, 0, and subtract what's in cell number 0. Binary numbers, 2 minus 1 gives a 1, and this is the correct answer. Okay. So again, the data structure now, a static data structure, has such a decision tree for each of the possible queries, right? So all the possible queries can have their own decision tree. And really, these decision trees live up to this definition that you read T cells on a query, right? That corresponds to following a path down the tree. And then you announce your answer based on everything you've seen, right? And this is because basically, if you're at a particular node in the decision tree, you only get to that node if you read a particular sequence of cells. So in some sense, you actually remember everything you've seen. And again, the cell that you read at each step may depend arbitrarily, right? It doesn't have to be a particular function that decides on where you go. It's just the bit patterns that lead you along different paths. Okay. So the decision tree now corresponding to the query 2, 1. Remember again, this would return whatever is in cell number j and subtract off what is in cell number I-1. So what you do is you start by reading what is in cell number 2. On this concrete input here in cell number 2, the bit pattern is 1, 0. So you follow the edge 1, 0 here. Then you would read what is in cell number 0 corresponding to the code here. So you would read what is in cell number 0. And here you see the bit pattern 0, 1. So now you're following this edge. And here you can say, whenever I end up in this particular node, I know that the contents of cell number 2 is 1, 0. The contents of cell number 0 is 0, 1. So if I want to execute this subtraction, I know I just should answer 1 in this case, right? So I just output 1, which is the correct answer to the query. Good. So in summary, a static data structure is, in the CellProbe model, a collection of S memory cells. Each of these memory cells stores W bits. W is at least the maximum of log S and log N. And each of the memory cells has an address from 0 to S-1, where S is the space usage of your data structure. The contents of the cells encodes the input data. And which basically just means that every possible input that you could receive to your data structure problem is just mapped to some memory representation. And here in this model, we don't care about how you compute this memory representation. There's just a mapping from inputs to memory representations. Okay. The queries are basically you read up to T memory cells and announce the answer based on the contents of everything you've seen, and you can remember everything you've seen. And the cell that you read at each step may depend arbitrarily on the query and the contents of previously read cells. Okay. And you can formalize this last part as depth T decision trees, having a particular depth T decision tree for every possible query you could ask. Okay. In the CellProbe model, we call reading these cells probing them. So from here on, we'll say we probe up to T memory cells, and the cell that we probe in each step may depend arbitrarily on the query and the contents of previously probe cells. This is where the name of the model comes from, the CellProbe model. Right. This model is very old, dates back to the 80s by Turing Award winner Andy Yao. It's a very clean model in some sense. In particular, what we're lower bounding when we prove lower bounds in this model is the number of memory accesses that your data structure is performing. And therefore also the number of clock cycles that you need, right? Because as we talked about, whenever the CPU has to access a memory cell, this is going to take some non-zero amount of time. In this model, we assume that the computer can perform arbitrary instructions on the cells, right? They're just represented by this decision tree, which means that if we can indeed prove lower bounds in this model, then the lower bounds will apply no matter what the computation device is, right? So I guess one very important thing to note here is that this model is not meant for developing data structures, right? Because it's a little weird to have these decision trees and allow arbitrary instructions. Because this is really not realistic that you have a giant decision tree for every possible query, right? Because in particular, if your query time is T, a depth T decision tree is really large, right? It has size 2 to the T times W. So it's exponential in the query time, the size of this tree. So you would not develop data structures in this model, right? But what you should have in mind is if I want to prove a lower bound, if I give more power to a data structure and I can still prove a lower bound, then the lower bound is just even stronger. The lower bound holds even if the data structure was super powerful. Right, so proving lower bounds in this model will mean that the lower bounds hold for all these computation devices. Right. So what's going to come in the following videos is really how do we prove lower bounds now in this CellProbe model. Right. So I hope that you'll watch these videos and learn more about this very interesting area of research.